Let's start with 12.1 Coulomb's law. We know that there are two kinds of charges, namely positive and negative charges. The charge on an electron is assumed to be negative and charge on a proton is positive. Moreover, we also learned that like charges repel each other and unlike charges attract each other. Now we investigate the quantitative nature of these forces. The first measurement of the force between electric charge was made in 1874-80 by Charles Coulomb, a French military engineer. On the basis of these measurements, he deduced a law known as Coulomb's law. It states that the force between two-point charges is directly proportional to the product of the magnitudes of charges and inversely proportional to the square of the distance between them. It is mathematically expressed as F is directly proportional to Q1 Q2 upon R square, and applying the K we get F is equals to K Q1 Q2 upon R square, where F is the magnitude of the mutual force that acts on each of the 2-point charges Q1 and Q2, and R is the distance between them. The force F always acts along the line joining the 2-point charges. K is the constant of proportionality. Its value depends upon the nature of the medium between two charges and system of units in which F, Q and R are measured. If the medium between the 2-point charges is free space and the system of units is SI, then K is represented as K is equals to 1 upon 4 pi epsilon naught, where epsilon naught is an electrical constant known as permittivity of free space. In SI units, the value is 8.85 into 10 raised to power minus 12 Newton meter square per Coulomb square inverse. Substituting the value of epsilon naught, the constant K upon 1 upon 4 pi epsilon naught gives us 9 into 10 raised to power 9 Newton meter square Coulomb square inverse. Thus, Coulomb's force in free spaces F is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. As stated earlier, Coulomb's force is mutual force. It means that if Q1 exerts a force on Q2, then Q2 also exerts an equal and opposite force on Q1. If we denote force exerted on Q2 by Q1 as F21 and that on charge Q1 due to Q2 as F12, then F12 is equals to minus F21. The magnitude of these two forces is the same and is given by equation 12.3. To represent the direction of these forces, we introduce unit vectors. If R21 is the unit vector directed from Q1 to Q2 and R12 is the unit vector directed from Q2 to Q1, then F21 becomes 1 upon 4 pi epsilon naught Q1 Q2 upon R square R21. F12 is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon R square R12. The forces F21 and F12 are shown in figure 12.2 A and B. It can be seen that R21 is equals to minus R12. So equations 12.5 shows that F21 is equals to minus F12. The sign of the charges in equation 12.5 A and B determine whether the forces are attractive or repulsive. We shall now consider the effect of a medium between the two charges upon the Coulomb's force. If the medium is an insulator, it is usually referred as dielectric. It has been found that the presence of a dielectric always reduces the electrostatic force as compared with that in free space by a certain factor, which is the constant for the given dielectric. This constant is known as relative permittivity and is represented by epsilon naught R. The values of the relative permittivity of different dielectrics are given in table 12.1. Thus, the Coulomb's force in a medium of relative permittivity is given by F is equals to 1 pi upon 4 pi epsilon naught R epsilon Q1 upon Q2 R square. It can be seen that in the table that epsilon naught R for air is 1.0006. This value is so close to 1 that with negligible error the equation 12.3 gives the electric force in air.